Now we're going to talk about deadlock, and specifically we're going to talk about it in reference to resources. If you were comfortable with the previous introduction to deadlock video, then you're ready to watch this video. We know what resources are as far as an operating system is concerned, but I'm going to break them down into two broad categories in this. The first category is reusable resources. These are resources that only a single process at a time can safely use, but that are not depleted by that use. So obvious candidates for these are many of the resources that we've already talked about, like processors, I/O channels, memory resources, devices, and data structures, for example, a file, a database, or a semaphore. The second category of resource is one that we've talked far less about so far, and that is the consumable resources. These are a resource that we can create more of and that we destroy when we utilize them, or we can destroy when we utilize them. So examples of consumable resources from an operating system perspective are things like interrupts, signals, messages, or information that might exist in an I/O buffer. These are things that processors or the operating system itself can produce and create, but which are often destroyed as a result of accessing that resource. We've already seen examples of deadlock occurring from accessing reusable resources, but I'd like to give another example. And that is an example where we have a reusable resource that is not binary like the previous resources we've talked about. And a good example for this is processors accessing memory. Let's imagine that we have two processors existing in a system where there is a total shared memory of 200 kilobytes. And let's imagine that each of the processors has some execution path where they do some execution, request a certain amount of memory, do some more execution, and request a different amount of memory. And the execution paths are different, and the two amounts that each process requests is different. What we see is that if both processes proceed past their first memory request and then arrive at their second memory request, we will have deadlock. Process P1 will request 80 kilobytes of memory, leaving a total of 120 kilobytes left in the shared pool. Process 2 requests 70 kilobytes of memory, leaving only 50 kilobytes left in the shared pool. At this point, neither process can have its request for memory satisfied by the operating system, and because neither process releases the memory that they already have, we end up in a deadlock scenario where neither process can continue. I'd also like to give an example of deadlock occurring as a result of consumable resource use. So let's imagine that we have processes which are generating messages and receiving messages. And we write our two processes so that they each try to receive a message from the other process and then send a message back to the other process. So P1 and P2 are both trying to send and receive messages from each other. But the ordering here is important. Both P1 and P2 want to receive a message from each other first, do some processing perhaps on that message, and then send another message, a new message, back to the other process. We have a candidate for deadlock here if both processes arrive at the receive call, and that receive call is a blocking operation, because both processes will block upon trying to receive that consumable resource, which is the form of a message, and will not be able to proceed to send a message back to the other process to unlock it. So we end up with deadlock here, even though the resource that we have can be produced. To represent these sort of situations a little bit more formally, we can use a kind of graph called a resource allocation graph. Now, when we say graph here, we don't mean plot, we mean graph in the discrete mathematics sense of nodes and edges. A resource allocation graph is a directed graph, and it represents a particular state of the system at a time in terms of its resources and its processes and the ownership of resources there. We represent all of the processes and resources as nodes, and in our particular case here, we're using slightly different nodes to represent resources and processes. We're using circular nodes to represent processes and squares to represent resources. What we're also doing is putting a little dot in the resources nodes to indicate multiplicity of that resource. So if we have a resource which can be accessed 3 times, it would be represented by a square with 3 dots in it. Now that'll be important for later. Obviously we have an example of this type that we might have multiple instances of, might be an I/O device that's allocated by some resource management module in the operating system. Now, if a process is currently requesting a resource, we draw a directed edge from that process to that resource. So in this case here, we're saying P1 is requesting a resource RA. If the resource or request is granted and the process has an instance of that resource, then we draw a directed edge from the dot inside the resource over to P1. So you could even imagine that the real directed graph is actually from these little dots, and that these resource nodes here are actually sort of container nodes. But it's not particularly important. So the key is we have resources and processes represented by nodes, and the directed edges represent either a process requesting a resource or a process holding a resource. If you remember back to our previous video, we had this example here of a scenario where we had potential deadlock and actual deadlock, and that was in the form of a 4-way intersection. So each of these cars is a process, and the 4 quadrants of the intersection are a resource, which can only be held by one process. So without any requests or allocation of resources, we would have a situation where we have 4 processes and 4 resources, each of which can only have 1 instance granted, because we can't have 2 cars in the same quadrant of the intersection, otherwise we have a crash. Once 4 cars arrive at the intersection, we have this resource allocation graph shown here. So P1, for instance, in order to progress through the intersection, requires access to quadrant A and quadrant B. So we have requests for resource A and a request for resource B. And you can see that the remainder of the requests are indicated here. Now let's imagine that process 1 has its request for resource A granted and moves into its first quadrant of the intersection. That would result in its request for resource A being granted. So this edge would disappear from the resource allocation graph, and we would end up with a new edge from the instance of that resource heading back up to process P1. And let's say that at the same time, or shortly thereafter, car 4 gets its request for resource D. Then again, we would see the same instance of this request edge no longer existing in the resource allocation graph, and a new edge from the instance of resource D back to process 4, indicating that process 1 holds resource A and process 4 holds the instance of resource D. Now in the second instance, where we have actual deadlock occurring, where all 4 processes have requested 1 resource but can no longer satisfy their second resource request, we have this resource allocation graph here, which shows an actual instance of deadlock. Now, you can verify that that is actually correct here, but one thing I would like to draw your attention to is the circular path of edges that we have here. We have a nice cycle through all of our resources here, and the key thing is that in none of these resource nodes is there a free copy of that resource that can be granted, allowing the deadlock to be resolved. Again, another quick example. This is a simpler version of the same deadlock. We have here a circular wait condition which is causing a deadlock. Process 1 is requesting resource A, which is held by process 2, which is requesting resource B, which is held by process 1. Now, if we had the exact same scenario here, but our resources had some multiplicity, we would have no deadlock occurring, because, for instance, this resource could be allocated back to process 2, resolving the circular wait, and then process 2 could complete itself, and even if we didn't have a multiplicity of resource A, for instance, this hold would eventually be released by process 2, allowing process 1 to continue on its merry way. What we now arrive at is a set of 4 conditions which are required for deadlock, and these conditions are necessary and sufficient. They are, for those of you who are unfamiliar with those terms, necessary in this case means that these conditions must be present. If any of these 4 conditions are not present, then we do not have a possibility of deadlock. Sufficient means that if these conditions are present, then we definitely have a deadlock. So the first is mutual exclusion. If only one process can use a resource at a particular time, then we have a case of mutual exclusion. The second condition is hold and wait. This describes the fact that when processes gain the resources that they have, they are able to hold on to those resources while they wait for future resources. The third condition is the lack of preemption. So in this case, we mean preemption in terms of preempting the hold on resources, not preemption in terms of execution. So what this means is that it is not possible for us to forcibly take a resource back from a process which is holding it. And the final condition is the one that we've seen a few examples of in this video so far, and that is the presence of a circular wait. Now, the thing is that these first conditions are actually quite desirable from certain points of view for an operating system. Mutual exclusion is a very important thing, and we introduced it for a good reason earlier in this in the course. If we don't have mutual exclusion, then we can end up with very unsafe processing situations. Hold and wait is important because if we don't have hold and wait, it is quite possible for processes to be constantly shuffling around with resources. Sometimes processes need multiple resources at the same time, and it can be quite slow for processes to simply try to access all the resources they need in one go until they're available. A lack of preemption on resources can also be desirable in terms of efficiency as well. And the fourth condition here is essentially a logical consequence of the first 3. When we have the first 3, it is possible for a circular wait to occur. And the circular wait itself is basically the definition of deadlock. So just remember, these are 4 necessary and sufficient conditions for deadlock. Hopefully this video hasn't been too confusing, but we've covered 3 important things. First is the broad categories of resources. Remember that we talked about consumable and reusable resources. We've talked about resource allocation graphs as a way of representing the state of a system in terms of processes and resources, what processes are requesting what resources and what processes hold resources. And then we finally arrived at the 4 necessary and sufficient conditions for deadlock to occur. And later in the course, in this week, when you're in your lectures learning about how we try to prevent or resolve deadlock, it all balances around eliminating or alleviating one of those 4 conditions.